focus on graphing exponential functions, we're going to do them the same way that we've done every other function. So our goal is going to be to have a parent function and then to adjust that parent function based on transformations. And the transformations are the same as how they worked before. If it's with x, it affects x. If it's not with x, like not in that part of the function, it changes y. And they all work the same way as before. Hi. I do. Do you need more than one? Just one? This one's like, the first one's like dry, so I'm going to give you two. Oh, it's juicy. There you go. Bye. Okay, so exponential functions don't need to be any more difficult than any other types of functions. The issue is the parents. So for quadratics, there's one parent function, right? Every time you're starting a quadratic, you start with this one parent function. It doesn't matter what else happens in the function. Same with cubics, square roots, and cube roots. The difference with logs and exponential functions is there's not one parent. There's one parent for every base. So like if you're using 2 to a power, that's a different parent than if you're using 3 to a power. That's a different parent than if you're using 4 to a power or 1/2 to a power. But we can build the parent function still fairly quickly, okay? So we're going to look real quick at some basic, sorry. I'm going to take it off of full screen because you guys can't see what I need you to see. Still can't see what I need you to see. So sad. So I'll make it big again since it doesn't matter. Okay, so this is going to be our growth graph. We're not going to emphasize, you're not going to have to answer a bunch of questions about growth versus decay. However, you just want to understand when the graph might look a little bit different. So your growth is if your base is something that gets bigger as you raise it to powers. So one example is using 2, okay? It doesn't have to be 2, but it could be 2. When I put higher powers on 2, 2 gets really big, right? Like 2 to the first is just 2, but then 2 to the second is 4, and 8, okay? And then 16 and 32, 64, it starts growing pretty rapidly. So that's why it's growth. Okay, so in other words, the base has to be bigger than 1 in your equation to be called growth. Okay, and if it's growth, you expect the bigger power to create bigger numbers unless it gets like flipped around or something like that. Okay, so our parent function, if we were doing y equals 2 to the x is a parent, but there are lots of exponential parents. What if it wasn't 2, like we said? What if it was 3, etc.? Basically, because we can plug in anything for exponents, you want to plug in the same basic 5 numbers you plugged in for cubics and for quadratics. That we just want things kind of centered around 0 to see what's going to happen. So we would plug in -2, -1, 0, 1, and 2. And then you have to remember what happens when you do that. So when you make an exponent of -2, what does negative do to your base? Okay. Good, yeah. Overall, it'll be 1/4. So when I make 2 to the -2 power, I get 1/4 because the negative flips it over, the 2 squares it. So this would be 1/4. What about when I plug in -1 as the exponent? 2 to the -1 power is equal to what? 1/2. Okay. And what's 2 to the 0 power? 1. And then they get a little simpler. 2 to the first power is 2. 2 to the second power is 4. Okay? So let's plot those points and see what they look like. So -2 is only at 1/4. -1 is at 1/2. 0, 1, 1, 2, and 2, 4. Now, if you guys remember from Algebra 2, exponential and log functions have asymptotes. So asymptotes are things we get closer and closer and closer to, but we never actually cross. And so here's the thing. You guys are calculating 2 to certain powers. Is there any exponent that you can put on 2 that will make this worth 0? Like 2 to that power equals 0. No, because remember we talked about this with logs, right? There's no exponent that turns things into 0, and there's no exponent that turns things negative. So in other words, if this is your entire function, you're never going to be able to get 0. You're never going to be able to get negative, okay? But you get really close to 0. Like right here, you're already at 1/4. If you plug in 2 to the -3rd, you get like 1/8, 1/16, 1/32, 1/64, 1/128th. It's getting really small numbers, but never zero and never negative. So that's why we say that this asymptote exists here. Okay? It's a boundary that we get closer and closer to, but we never actually cross. So our curve looks like this. Okay? So with exponential functions, our asymptotes are these horizontal lines because we can plug in anything, but we can't get certain things. I can't get 0 as an answer, and I can't get negative, so it's the y's that can't reach here or below. Okay? So the asymptote is at the equation y equals 0. Okay? And all the exponential curves have some same features and follow the same types of rules. So the only difference with decay is the direction that you'll see it go. So if you make the base smaller than 1, but we don't use negative bases, so not below 0, but just smaller than 1. So let's say for our equation we used 1/2. Some of the rules still apply. You're taking 1/2 and you're raising it to some power. But again, no exponents can make something equal to 0, and they still can't make it negative. So you're still never going to be able to answer this question, and you're still going to have this boundary here. So you're still going to have this asymptote at 0. The only difference is the values you get when you plug stuff in. The bigger numbers you plug in as exponents on 1/2, 1/2 to the first power would be 1/2. What would 1/2 to the second power be? 1/4. 1/2 to the third power? 1/8. So when I make the exponent bigger in this case, it's actually, the answer is getting smaller because it's a fraction in there that's less than 1. So when we build our parent for here, we can use the same values, but it's kind of weird. The bigger numbers that we put on the exponent actually made it smaller. So like 1/2 to the first power was 1/2. 1/2 to the second power was 1/4. 1/2 to the 0 power is still 1. What's 1/2 if you put a -1 power on it? Nothing negative. Remember, negative exponent doesn't turn it negative. It flips it over with its reciprocal. So if you have 1/2 over here to the -1 power, it's 1/2, but it's getting flipped to its reciprocal, which will end up being 2. You were right. Some other people didn't say that. What about 1/2 to the -2 power? 4, right? Because it flips it over and turns it to 2 and then squares it. So we get 4. So this one kind of looks opposite-ish of the other in a way, that like you plug in the negative exponents, it actually made it bigger. And when you plugged in the large positive exponents, because it was a fraction, it actually made it smaller. So it just kind of makes the curve go this way. So just be aware that depending on what you have, your parent function could go either way. But notice what the parent functions have in common. So every exponential function you get, you can make the parent using these 5x values. Okay? That's important for us. Also, all the exponential functions have their asymptote at y equals 0. What's the only transformation that will have this asymptote change? So if we reflect it, will it change the asymptote? If you flip over this, it will still be there. If we flip this way, it will still be there. So reflections are not going to change your asymptote. Okay? Stretches and compressions measure how far you are away from an axis. If we stretch and compress it this way, it's already there, and it's just going to stretch and compress, okay? If we stretch and compress it this way, it's on the axis, so it doesn't move. So stretches and compressions don't change your asymptote. What's the only thing that will change this asymptote's location on the graph? Summer? Yeah. So in this case, the K, shifting it up and down, okay? Functions. Do you know how to build them? That they're all going to have an asymptote at y equals 0. So we're going to start with these charts every time and keep in mind that we have these asymptotes. And then we're going to do our transformations just like we've always done. Okay? Hopefully no different. All right? So we're going to try a few examples today, and that's going to be our goal, just to get the graphs done. Okay? All right. So here's our first one. So again, we want to start with a parent function. Like I already know this exponential thing that's simple, and then I'm going to change it by doing this and this and this, or however many changes that there are, okay? So first, when you look at the function, what is our parent function? So these aren't as simple. Remember, you have to actually choose. It's something to the power of x. So what's being raised to the power of something in our function? What's the base of the function? 2. So 2 is not a transformation. Do you guys understand? 2 is not a stretch, a compression. It's not a h. It's not a k. 2 is just part of the parent function. So that part is not a transformation. It's part of what we have in the beginning. And then you would build this parent function by plugging in these same values, since we can plug in anything we want to exponentials and calculate them. And we just used 2 in our example, so we should be okay with the outcomes here. And then I like to write my asymptote too, because we can actually just change the asymptote just like we change everything in our transformations. Like, see how the asymptote is a y value of 0, y equals 0? You can do to this all the things you do to your y and just get your new asymptote and transform it just like we transform everything else. So if you guys like that, you can do that. Otherwise, you can just use your k value to adjust where it is. Oh, thank you. Good job, Laurel. Okay, are you guys okay with what I fixed on there? Did you guys see? I put 0, 0, bad habit, right, from all of our other functions, but it's 0, 1 now. So I have my parent function and I have my asymptote. What are the transformations that are happening here? I'm going to write them down because we're supposed to be able to write them down. You guys struggle with that a little bit, so I'm just going to reiterate it while we go through them. Summer?
Is it like vertical?
Good. So the 3 is not affecting the x. Do you guys see where the stuff would have to be if we were going to include it with our x? Our h and our b value that are changing x, they would have to be up there in the exponent with x. That's what it means in this function to affect x. So that -3 that's out there, it's not changing x, it's changing y, which makes it vertical. So Summer said vertical stretch, okay? And she is right, because in our chart, when we make our new function, y is going to be multiplied by 3, and that's the vertical stretch that's happening. Okay? Then the other thing we need to account for is the negative. Okay? In our chart, it also shows up as just changing the y values to their opposite. And what do we call that transformation? Okay? So it's a reflection, and then over which axis? Good. It's changing y, but when you change y's from positive to negative or from negative to positive, you flip over the x. So this would be a reflection over the x-axis. Okay. And there are no horizontal changes, because look at the exponent. Nothing is happening to x in the exponent. It's just x, just like it was in the parent function. Okay. So our new chart is going to have unchanged x values because there's no horizontal transformations. And then in our y values, we're going to take them all and multiply them by -3. Okay? So 1/4 times -3 is -3/4, -3/2, or -1.5, -3, -6, -12. And then I want where my new asymptote is. Okay? So you guys have 2 ways of figuring this out. Either recognizing, like we talked about in the parent function, that the only thing that's going to change your asymptote, move it up or down, is the k value. Was there any k value in this equation? Anything being added or subtracted onto the y values? There's nothing, so it should not change. If that's hard for you to remember, because your asymptote is a y, you can literally do exactly what you're doing to the y's. It started at 0. If you take -3 times 0, then you still get 0. Okay? So if you're unsure, you can use your transformations, and if you know it's a y, you just keep working with the y values. Okay? And then we'll just sketch these points, and we should get something that looks like an exponential curve. So our y equals 0 is still our asymptote. So that's this horizontal line here. And then we're just going to plot those points. So -2, -3/4, -1, -1.5, 0, -3, 1, -6. And then 2, negative 12 is off my graph, but I can see the curve here and I can draw it in. Okay. And it makes sense that it's on the other side of the asymptote than we're used to because of that reflection that happened. Okay. Is this all right with everybody? All right, so I'm going to have you guys try one in your groups. All right, so this has 1/2 as the parent. Before you guys start, I'm going to rewrite it up here. Okay, so your parent chart should use 1/2 as the base. We made it in our decay graph, so you should have that written somewhere. And then you want to try and make a new chart with the transformations and figure out where the asymptote is. So see how far you guys can get, and then we're going to try and check it together. Okay? Everything that is in the exponent, that's your B, and that's your X minus H group. Okay? So my B value is -3, which means what I'm actually going to do to X is change the signs with the negative, but because the B is 3, remember how we use the B value, we'll actually be multiplying our X's by 1/3. Okay? And then this says X minus 1. That's our X minus H quantity. So what actually is the value of H? +1, so we're actually going to the right one. Is everybody okay with how we set it up? So we're looking at the exponent now just like we would look at the stuff underneath the radical. It's not pretty, I get it. We have to do some fraction stuff. We'll deal with it, okay? So now we're going to go ahead and we're going to do the arithmetic to change these, okay? If you have to, do the fraction math off to the side. So when I plug in -2, that was my first X value. It's getting multiplied by -1/3 and added 1. So -2 times -1/3 is 2/3. +1. They're both positive. I can just write 1 2/3. As long as both things are positive or negative, you can just add them together. But you don't want to do that if it was like 4/3, because 4/3 is like more than 1. You don't want like 1 and a fraction that's more than 1. That's going to be probably mess you up when you go to graph it. Okay? So when I do -1, -1 times 1/3 is 1/3. +1. Again, they're both positive, so I can just think of that as 1 1/3. I'm normally not a huge fan of mixed numbers if I have to like take them later and add and subtract stuff, but we don't have to do that, right? These are the points we want to graph. A mixed number is actually friendly when you want to graph because you know to go like 1 and like 1/3 further, right? So then our X value of 0, okay, would be 0 + 1, so we just have 1. Okay. When our X value is 1, -1/3 times 1 is -1/3. And here's where you guys have to be careful, okay? This is now not 1 1/3. So you guys need to do this one of two ways, and it just depends on how good you are at understanding fractional parts of numbers. This is a +1 and a -1/3. So I'm pretty good at going 1 is made up of 3/3. And then I have to take away one of them because they're different signs. So I'm left with 2/3 positive. I'm pretty good at doing that. But clearly, I've had a lot of fraction experience in my life, right? If you're not good at doing that, you need to just take the time to do -1/3 + 1 and think of 1 as a fraction and add fractions like you would with common denominators. So to make a common denominator, I have to multiply by 3. So now it's thirds in the denominator, and -1 + 3 makes 2 in the numerator, and I get 2/3. This does not take you guys that long. It takes like 30 seconds or something like that, and it is the difference between you having the correct number to plot here and not. So if it takes you a little extra time, it does. Totally depends on your fraction experience, whether you look at this and go, I know that's 2/3, or I need to go do this, okay? And all of us need to go do this at some point. Right? So there's no shame in this. I do this all the time. So don't think like you're not supposed to be doing this. You're just supposed to know. No, if that's how you get it right, that's how you're supposed to be doing it. Okay? So then we have 2. -1/3 times 2 is -2/3 + 1. Again, they're different signs. So either I'm really comfortable with fractions and I understand this is 1/3, or I come over here and do -2/3 + 1, and I get 1/3. Okay? All right, the y's are a lot simpler for us in this case. We just have to subtract 1 from all of the values. Well, here it might get a little bit. So 4 - 1 2 minus 1, 1 minus 1. And then you guys have to figure out the fractional parts again. So most of you guys are pretty good with halves. So half minus 1 gives us negative half. Quarter minus 1, again, because of our money, some of you are pretty good with quarters. But if you're not, then you're just coming over here and writing it like this. Make common denominators. It's fourths, and you have 1 minus 4, so that's negative 3. And then you adjust your asymptote the same way. You either know right away that it's at negative 1 because that's the k value and you understand transformations and that's the only way to move it, or because you know it started at y equals 0 because it's a y. Take your y transformations to adjust your asymptote. So your asymptote used to be 0, but now you're subtracting 1 from it, and that makes it at negative 1. Okay? So I'm going to go ahead and start with drawing my asymptote in at negative 1. And then I'm going to plot all those points, and they should make some sort of exponential curve if I did it correctly. Okay? So 1 2/3, 3, 1 1/3, 1, 1 0, 2/3 negative half, and 1/3 negative 3. All right, so I got something that looks like this. This looks like it's curving towards the axis, so then I'm able to fill it in. Well, it's climbing like that. This part is going towards the asymptote. Okay, you shouldn't cross the asymptote. Okay. That's why it's there. Remember, it's like a boundary for us. So questions about this? Yeah, Candy. So the asymptote is normally at 0. Since it's on an axis originally, reflections, stretches, and compressions don't change it. So the only thing that can move the asymptote is shifting up or down. So one way to find your asymptote is to understand that and then know that this number here is always the shift up or down. So because it was a shift down 1, that's why my asymptote moved down 1. The other way is to know the equation of the asymptote. If you know that it's y equals 0, you can just take 0, and since it's a y that's equal to 0, you can just adjust it by doing the same transformations that you do here, and you can see your new y value of your asymptote. Okay? All right, any questions about this? Again, the b value makes it a little more complicated, right? We have to remember to use the reciprocal and where we're looking at that, but the same types of transformations that we've done with everything else before. Okay? All right, so let's try one more. I think we have time for one more. I'm checking. 52. Yeah. So that one's friendly. It just has a new parent function. All right, so work on this one for like 5 minutes, and then I'll put up so I can make sure that you get the answer before like our homeroom period and stuff like that works, okay? New parent function, though, make sure you pay attention to the base, okay? Okay, check and see how far you got. So this is my parent function table with an asymptote at y equals 0. I used 4 as the base for my parent function. So same x values to plug in, but these numbers now based on powers of 4. Okay. For my transformations, there are only 2. So remember now, your exponent position is where your b and your h would be. There's nothing multiplying x, so there's no b value, but there is a x minus 2 in the exponent. So that's like my x minus h, which means my h value is a positive 2 or shifts it 2 to the right. My k value is that plus 1 at the end. So vertically, I'm shifting everything up 1. So these should have been the transformations we were looking for. There's just 2 translations, to the right 2 and up 1. And then I'm going to take all of these and add 2 to them to shift them right 2. So this will be 0, 1, 2, 3, 4. And then for my y values, I'm going to take them and add 1 to all of them to shift them up 1. So 1 and 1/16. Again, I'm able to get these quickly because they're the same sign. 1 plus 1/4 is 1 and 1/4. 2, 5, 17. and my asymptote. Yeah, Chloe. Yeah, totally. Yeah, as long as you know where that is. Okay, as long as you can figure it out. And then for your asymptote, again, 2 ways. You either understand a shift up 1 moved your asymptote up 1 and you know that it's y equals 1. If you're unsure about that, you just notice it's a y and you take the 0 and you adjust it just like you did here. So it would be 0 plus 1, which would now equal 1 for your asymptote. And make sure you write those equations as y equals 1 because the log equations will have asymptotes that go the other way. And those are x equals something, so you have to make sure you include that variable part. For this one. Because the k value is the only thing that will shift it up. So go ahead and plot your asymptote, and then you should be able to plot your points and see the exponential curve. So 0 is 1 and 1/16, really close. 1 is 1 and 1/4. 2, 2. 3, 5. 4, 17 is too far. So you should see a curve like that. Okay? So same idea as before. So the things I'm noticing that you guys are struggling with are these. Number 1, identify your parent function. Make sure you're building the table around that number, and then you don't use that number in the transformations. Like nothing over here got multiplied by 4 or anything because of the 4, okay? But I had to make sure I used 4 to get these numbers here. So really separate what your parent function is from the transformations. And then number 2, train yourself that in an exponential function, all the horizontal transformations are up here, and then you're still going to treat your b value and your h value just as you did before. Those are the questions that most people were asking me as I walked around, okay? So tomorrow, we're going to work on log functions, and then we're just going to use Wednesday and Thursday and Friday to practice those things, okay? And then Monday to review, and your test on Tuesday, okay? So all the functions, finding intercepts of them, tables, graphs, transformations, okay? Domains and ranges, h's and k's, yeah. Say it again, sorry. Yeah, so what we're going to do is this. So on Friday, I'll introduce it because we were going to work on it all next week. Now we'll only work on it Wednesday, Thursday, Friday, and the following week, 1 day. But that's still 4 days in class, and then it's not due till the end of that week. So you have like 3 or 4 more days to do it. You'll have enough time, but I will introduce it on Friday so that those of you that feel confident in the material can work on the project ahead of time if you want. Okay?